Hello everyone, welcome to the 7th lecture of the series on AI using Python. In this lecture, we will discuss about neural network or NN and its basic concepts. Neural networks or artificial neural networks are built of artificial neurons, which we also call as perceptrons or simply as neurons. Neurons are the data processing units in a neural network and are arranged in layers. So a neural network can be considered as a series of layers which transform the input data into some outputs. In general, a neural network can be considered as a composite function from a mathematical point of view. We have a composite function is a composition of more than one functions. So in a composite function, the output of the first function will be the input of second function, and the output of second function will be the input of the third function, and so on. Now, when it comes to a neural network, we have the general structure of a neural network can be represented as in this equation, where x is the input data, y hat is the predicted output, f0, f1 up to fl plus 1 are the layers of the neural network. So here this is in the form of a composite function where the output of f0 will be the input of f1 and the output of f1 will be the input of f2 and so on. We have L plus 2 number of layers in the neural network, in which the first layer we call as the input layer, which is denoted by f0 here, and the last layer we call as the output layer, which is denoted by fl plus 1, and the layers in between we call as the hidden layers. Here this f1 up to fl are corresponding to the hidden layers, and here we have L number of hidden layers. We have each of these functions fi are also composite functions, which can be represented as in this equation. This means each of these fi are built of composition of a linear mapping of the form ax plus b and a nonlinear function which we represented by sigma, and this is called as the activation function. So we can see that each function fi consists of two components, where the first one is an affine function which is in the form of ax plus b. This basically represents a linear mapping. And the second component is called as an activation function, which is basically a nonlinear mapping. And we can have different choices for activation functions, such as step function, rectified linear unit or ReLU function, sigmoid function, etc. And also we can select an activation function in the form of a linear function. In that case, the function fi becomes a linear mapping. In this lecture, we will be focusing on a particular activation function called as rectified linear unit or ReLU, which is defined as in this equation. And the ReLU function implements a half-wave rectifier which basically passes the positive input and blocks the negative input. The output of the ReLU function will be 0 if the input is negative, and for positive inputs, the output is same as the input. And this we can also represent it as maximum of 0, x. So in which case, if x is negative, the output of this function will be 0. This figure shows a general representation of a neural network, which are built of neuron. And here we denote a neuron by a red circle, and a layer can be considered as a collection of neurons which takes the same inputs. Here, these neurons are also composite functions which are of the form sigma of ax plus b. And this neuron can be considered as a scalar valued function, or in other words, the output will be a scalar. And a layer will contains a collection of neurons. So a layer can be considered as a vector valued function. And in a neural network, we can have three types of layers, which are input layer, hidden layer, and output layer. Normally, we have only one input and output layers, whereas we can have more than one hidden layers. So here, each of these hidden layer can be represented mathematically using a function f1 up to fl. And here, this input layer we can represent by a function f0, and the output layer we can represent by a function fl plus 1. So with this notation, we can have L plus 2 number of layers in a neural network, and L can be any finite natural number. Next, we can illustrate the basic idea of neural network, in which we start with a neural network with one neuron per layer, and it can be represented as in this figure, where we have only one neuron in each layer. Here, this input and output are considered as univariate data, and each of these functions f1 up to fl are scalar valued functions or real valued functions. We can denote the outputs of the hidden layers as y1, y2 up to yl, where the capital L denotes the number of hidden layers. And we have seen that each of these functions will be in the form of sigma of ax plus b, where sigma is the activation function. And in these examples, we will be considering ReLU as the activation function. First, let's plot the graph of the ReLU function. And for that, we are generating the input data x as 100 equally spaced data points between -10 and 10. And the output y is initialized as zeros. And we are using a for loop for updating the output, in which for each sample of the input data xi, we compute the output yi as maximum of xi, 0. This means if the input is negative, the output of this function or y of I will be 0. And if the input is positive, then y of I will be equal to x of I. Now we can plot x versus y, which gives the plot as shown in this figure. So here this line is folded at x equal to 0. And in this region, the output is 0. And in this region, output is equal to x. Next, we can see how ReLU of ax plus b will look like. And for that, we use the same input. And the output y of I is generated as maximum of 2xi plus 1, 0. And here, if 2x of I plus 1 is negative, then the output y of I is equal to 0. And if this term is greater than 0, then the output y of I will be equal to 2 into x of I plus 1. Now we can plot x versus y, and this gives the plot as shown in this figure, which is also like a folded line. But here this folding is taking place at x equal to minus 0.5. This is because of the reason that we have 2x plus 1 will be equal to 0 at x equal to minus 0.5. For all the values of x which is greater than minus 0.5, 2x plus 1 is greater than 0. And because of that, the output y of I will be equal to 2x plus 1. Now, if we change this intercept 1 into some other value, let's say 5, then we can see that the zero crossing point is also changing because this line crosses 0 at x equal to minus 2.5. And similarly, if we change this to minus 5, we can see that the line gets folded at x equal to plus 2.5 and so on. Similarly, we can consider another example in which the linear mapping is defined by minus x minus 2 and the output y of I is computed as maximum of minus x minus 2, 0. Now, if you plot x versus y, we get the output as shown in this figure. Since here we have introduced a negative slope to this line, we have this linear portion will be like this. And in this equation, we can see that minus x minus 2 will cross 0 at x equal to minus 2. Therefore, if x is greater than minus 2, this term will be negative. Therefore, the output of this equation will be equal to 0. And if x is less than minus 2, the output is defined by this linear relationship. So far, we have considered is a neural network with one layer, which has only one neuron. Now we can add more layers to this network and see what possibilities it can bring. And for that, we are considering an example in which the input x is consist of 100 equally spaced data points between minus 10 and 10. And the output of the first layer we denote as y1. And here the y1 is defined as maximum of 2x plus 1, 0. So we have y1 is equal to ReLU of 2x plus 1. And y2 is equal to ReLU of minus 0.1 y1 plus 1.5. And y3 is equal to ReLU of minus 0.3 y2 plus 0.5. And here we can see that each of these layers are in the form of sigma of ax plus b. And also the output of this layer, which is y1, will be the input of the second layer. And the output of this layer, which is y2, will be the input of the third layer. And here the output of the third layer we are considering as the output of the neural network. And we are denoting it as y. Now we can plot x versus y, which gives the plot as shown in this figure, where we can see that the line has two folds. And here we have y1 is equal to ReLU of 2x plus 1, for which the plot was a folded line with one fold, which we have seen earlier. And we can also see it here by just plotting x versus y1. which gives the plot as shown in this figure. Now we can plot x versus y2, which is a folded line with two folds. Now we can plot x versus y3 or x versus y, which will be a folded line with again two folds. So in the case of y3, we can expect a line with three folds, but actually what we are getting is a line with two folds. If we were able to get a folded line with three folds here, then we can possibly say that when we are increasing the number of layers, we can get more number of folds in the line, and thereby we can generate more complex structures. So here, if we can able to rotate this portion by some means, then we can introduce some folds here by using the ReLU function. So what we are interested is, can we rotate this portion using a linear mapping? Definitely we can rotate this portion, since if we multiply this with a weight a greater than 1, it will rotate counterclockwise direction, and if a is less than 1, it will rotate clockwise. And using the bias or the B term, we can shift this portion vertically upwards in the case of positive bias and vertically downwards in the case of negative bias. However, when it comes to this portion or this portion, it has a constant output value for each input in this range. So if you multiply this constant output with a weight a greater than 1, it will scale up and this portion will shift vertically upwards. And for a less than 1, this portion will shift vertically downwards. So this portion, the weight a does not have any influence. Or in other words, it has the same influence or effect as the bias. Therefore, even if here we add more number of layers like y4, y5, etc., each of their output can have at most two number of folds. Therefore, in the case of a neural network that has one neuron per layer and a ReLU activation function, we can have three possible outputs, which are a straight line with arbitrary slope, a folded line with one fold, and a folded line with two folds. And this idea is illustrated here, in which we repeat the example and plotted x versus 2x plus 1, x versus y1, and x versus y. And here we can see x versus 2x plus 1 will be a straight line, and x versus y1 will be a one folded line, and x versus y will be a two folded line. Now the question is, what we can possibly do to rotate this portion or introduce some folds in this portion. And the possible answer is, we can add more number of neurons in each layer. So next, we are illustrating a neural network with more than one neuron per layer. And to simplify the illustration, we are considering only one hidden layer. So here in this hidden layer, we can have more than one neurons. And the output of this first neuron we can call as y11, and this is y12, and so on. Here, each of these outputs y1j will be in the form of sigma of ax plus b, where sigma is the activation function. And in the illustration, we will be using a ReLU function as the activation function. So here, as in the previous example, the input data x consists of 100 equally spaced data points between -10 and 10. Now, the output of the first neuron in the first layer, or y11, is defined as ReLU of 2x plus 1. And similarly, the output of the second neuron in the first layer is denoted as y12, which is defined as ReLU of -x minus 2. And then we define the output y as y11 plus y12. And we can plot x versus y, which gives the output as shown in this figure. In the previous examples, we had seen the individual plots of y11 and y12. Now here the output y is obtained by adding y11 and y12. Next, we can add one more neuron and consider an example with three neurons, in which y11 is defined as ReLU of 3x plus 1, y12 is defined as ReLU of minus 0.5x plus 1.5, and y13 is defined as ReLU of 0.5x minus 1.5. And the output y is defined as y11 plus y12 plus y13. Then if we plot x versus y, we get a plot as shown in this figure. Now by changing a and b, we can fold this line at different points. For example, if we change this to minus 0.5, we can see that the curve will changes like this. Here we can observe that we have three folds in this line. One is at this point, one is here, and one is here. And similarly, if we change this to some other values, we can see that the outputs are also changing. So here also we have three folds. One is at this point, one is at this point, and one is at this point. So this shows that by adding more and more neurons, we can add more folds to the line. And this folded line we can also call as a piecewise linear curve. Therefore, with a ReLU activation function, we can obtain a piecewise linear approximation of a continuous function. And with sufficient number of neurons, we can approximate any arbitrary function using a neural network. And we can also use other activation functions like tanh, sigmoid, etc., which gives smooth approximations. This means we can have smooth bends instead of folds. We will discuss more about activation functions and the various possibilities it can have in the upcoming lectures. With that, we come to the end of this lecture, and thank you.